Hello and welcome, my name is James Leach, and in this video we'll be elucidating 4 types of motion with constant acceleration and how the MCAT will test them. Those 4 prevalent applications of motion with constant acceleration are the cases of linear motion, projectile motion, the case of an object being drawn down an inclined plane, and the special case of centripetal acceleration. Another important note before we carry on here is that air resistance and friction are considered negligible on the MCAT unless you are explicitly told otherwise.
Our goal through this review is to be able to recognize and calculate values for the behavior of objects as they undergo constant acceleration in one of the aforementioned ways. Along with the common inclined plane you see on your screen, you may also be asked to navigate a question involving objects in free fall, as we'll see right now, in our overview of linear motion with constant acceleration. As in the case of this ball moving downwards, when a force is applied, its acceleration vector points in the same direction as its velocity vector. In other words, it accelerates in the same direction as it moves. However, acceleration in the exact opposite direction of motion is still constant acceleration and linear motion. Thus, the overarching rule we can apply is that acceleration is along the line of motion. It's worth mentioning as well that when an object is not accelerating, or moving with constant velocity, it is still undergoing constant acceleration. In that case, acceleration is just 0. Now let's say this ball is being dropped out of midair. As it plummets towards the Earth, it undergoes constant acceleration due to gravity in what we call free fall. Never forget about the force of gravity on MCAT physics problems. Let's use this common case to explore the 4 major equations you need to have in your back pocket for MCAT kinematics, referred to affectionately as VAT, VAX, and TAX. Let's first check out this one. We call it VAT for the variables that appear on the right side of the equation. What do those variables mean? Well, v or v final is the final velocity of the object, which in the case of collisions is 0. V naught or v initial is the initial velocity of the object, which in this case of free fall is 0. A is the constant acceleration of the object, and t is the time over which the motion is occurring, or the time it takes for the object to accelerate from v initial to v final. VAX is the next equation we'll look at, and notice that it includes a new variable, x, or displacement, and is conspicuously missing t. Thus, when you are given or asked to solve for x, VAT is not going to help much. Likewise, if you don't know or need to solve for t, VAX isn't particularly helpful. This leads to TAX, or TAX, which is absent final velocity. TAX, as the name suggests, includes t, a, and x. Notice that it is missing final velocity, which means that this is the equation to use when final velocity is unknown and unasked for. Finally, this last equation excludes acceleration altogether, which seems kind of peculiar given the fact that acceleration is the focus of this video. What v bar represents is the average velocity over the period of acceleration being looked at. If you know the initial and final velocities, you can just average the two of those values because we are dealing with uniform acceleration, an object whose velocity is increasing or decreasing at a consistent rate. However, do not try to use this if acceleration is not constant. Let's work this example. The first thing we need to do is assess what variables we have and what variables we need to solve for before we decide which equation will help us. If the ball is dropped, it is initially at rest with v initial of 0. Gravity is the force acting, so acceleration is 10 meters per second squared. We're also given how far the ball falls, 1.25 meters. And lastly, we need to solve for its final velocity. Based on the variables we've been given and the one we need to find, one of these equations is more appropriate than the others to use for this problem. VAX includes the 4 variables we have or need to find, so let's use it. Let's sub our numbers into the equation. That initial velocity disappears, and we can calculate that 2ax term pretty quickly. Lastly, we take the square root of both sides and come up with 5 meters per second as our final velocity. As in the case of free fall, all linear motion is one-dimensional. That is, we only have to consider its motion in one direction. Things aren't always that simple, however. In projectile motion, the motion of an object in both the vertical and horizontal planes must be considered. Let's take the case of a ball being thrown out of the window. It seems clear enough that the ball has independent vertical and horizontal displacements. The ball falls only so far, or flies horizontally only so far. However, it is important to recognize that we must do the same thing for velocity vectors by breaking them into the x and y components. On that note, only the vertical component is affected by g. The horizontal component would be affected by air resistance, though air resistance is usually considered negligible on the MCAT. Enough talking about that, let's apply this knowledge to a real situation. The first thing to note is that we still apply our kinematics equations, but they only apply to motion in one dimension, hence why we have to break everything into component vectors. Here's our situation then. As with so many other topics in physics, triangles and trigonometry will be your best friend here. The ball is lobbed at a 45-degree angle, meaning it flies upwards before plummeting to the ground. If we want to find the maximum height of the ball, how far away from the building it lands, or how long it takes to get anywhere, we have to resolve velocity into its components. Since we know the initial velocity of the 45-degree throw, let's label it on our triangle. From here, the other two sides of the triangle, or the horizontal and vertical components of that initial velocity, must be labeled. To solve for the vertical component of velocity, or Vy, the component that is affected by gravity, we apply sine theta to find the side of the triangle opposite the known angle. This value must be known in order to determine the maximum height the ball reaches, how long it takes to get there, and how long it takes to hit the ground. To solve for the horizontal component of velocity, which will help us find how far away from the building the ball will land if we know time, we use cosine of the known angle to find the side adjacent to the known angle. Let's jump back to motion in one plane now, in this case, an inclined plane. The major difference between this example and linear motion as reviewed earlier is that the largest force, the force of gravity, does not point in the same direction as the resultant velocity vector. As such, we have a bit of trig to do before applying the kinematics equations here. The normal force is a contact force exerted by a surface on an object and always points out perpendicular to the plane of that surface. What we are really interested in finding, however, is the component of the gravitational force pointing down the incline in the direction of motion, because that is the force which causes acceleration to occur. To do this, we go back to trig to resolve the force of gravity into its components. Note that friction can also play a role in inclined planes and will point, as it always does, in the direction opposite motion. Problems like this become much simpler when we bring in a triangle with FG as the hypotenuse. This triangle must also incorporate the known angle theta and, most importantly, the value we're trying to solve for, F parallel. Let's pull away all the extra pieces for a second here and figure out our trig. Applying good old SOHCAHTOA again, we see that we need to use the sine of our known angle as it incorporates both FG and F parallel to the surface of the plane. Rearranging that trusty old formula and subbing mass times gravity in for FG, we see that the component of gravity pointing down the incline can always be found with mg sine theta, if the angle of the incline is known. To find the normal force, we apply similar principles. If you are asked to solve for the normal force instead, it is found using the formula mg cosine theta. Deviating a bit from the old kinematics equations, let's look at the unique case of circular motion, where the kinematics equations are largely unhelpful. At any isolated moment, the car's velocity is in a direction tangential to the circular path it is following. So we must consider what is keeping the object moving along its path. There has to be some force manipulating the path of the object, and in the case of uniform circular motion, that is the centripetal force. Because the acceleration vector and velocity vector are tangent to one another, the car is not moving around the circle more quickly at any given point. It is moving with uniform velocity. The force in this case causes acceleration that is also tangent to the velocity vector, its effect being that the car is held on the circular path. Centripetal force is calculated as seen on your screen, which perhaps makes a little more sense in terms of Newton's laws, where F equals ma, when we see that centripetal acceleration is just v squared over r. Looking at the force equation again, it is just mass times acceleration. Now let's get down to applying these concepts to some problems. Try this one on free fall first. First, we need to think about what affects acceleration. Well, the net force on the object causing the acceleration is a good place to start. What forces act on an object in free fall? Well, gravity is the big one. You may remember physics professors demonstrating that a tennis ball and bowling ball falling from the same height will reach the ground at the same time. Well, from this we learn that the force of gravity is not dependent upon the mass of the object falling. Increasing speed is expected for an object hurtling towards the Earth. Decreasing speed cannot happen without some phenomenal occurrence, and even then, it could still be constant deceleration. However, when air resistance is non-negligible, its force vector points opposite the direction of motion and increases as the object falls faster until the object eventually reaches terminal velocity, where the upwards and downwards forces are equal and the object is no longer accelerating. In this case, the object cannot be experiencing constant acceleration. Try this one on projectile motion now. The first thing that needs to be done is to draw out our triangle and figure out that we need to utilize the sine function of our known angle. Doing so, we find a vertical component of velocity equal to 4 meters per second. Now that we know the initial velocity in the vertical plane, the acceleration due to gravity, and the final velocity, which has to be 0 as the object is changing directions at its maximum height, we see that VAX is the formula which will be most helpful to us. Subbing in values and rearranging to solve for x2, or the maximum height above the initial height, we find 0.8 meters. Is that the correct answer though? No, definitely not. The ball's height is not 0.8 meters at that moment. It's 0.8 meters above its initial height, which was 6.8 meters. So, the height at that moment is 6.8 plus 0.8, or 7.6 meters, which corresponds with answer choice B. Let's apply some more kinematics to the inclined plane. Priority number 1, as always, is to hammer out a force diagram for this system, including the friction force, the gravitational force, and mg sine theta, or F parallel. Let's sub in some numbers for the values we know, Fn, Fg, and theta. In order to find the final velocity, we need to find acceleration, as it is common through VAT, VAX, and VAT. Acceleration, of course, depends upon the net force acting in the direction of motion, which is downward along the incline. The two forces acting along that plane are mg sine theta and friction, so we must find their sum. Given that friction is opposite the direction of motion, we'll subtract it from mg sine theta to find 31.5 newtons as our net force. As mentioned, we found F in order to find A, so let's do that using good old F equals ma. We can rearrange that to A equals F over m, or acceleration equals force over mass, in order to find acceleration. In doing so, we find 5.25 meters per second squared, or some approximation thereabouts. We now know initial velocity, acceleration, and displacement, so let's use VAX again. Working through VAX, we can approximate an answer of about 5.5 meters per second, which lines up with answer choice A. This last question deals with uniform circular motion. Give it a shot. This one is best dealt with by assessing which of the answers are true. A, we definitely know to be true. The velocity vector is tangent to the acceleration vector, so the resultant path definitely does not align with the acceleration vector. Centripetal force equals mass times centripetal acceleration, which equals 40 times 200. Doing that one in your head might be easier by transferring the 0 and dealing with 4 times 2000, which equals 8,000 newtons. So B checks out. C, like A, is a central tenet of uniform circular motion. The force does not cause a change in the tangential velocity. It just holds the object on its path. D, on the other hand, is definitely a miscalculation. If centripetal acceleration equals 40 meters per second squared, and we know the formula for that is v squared over r, then 40 times the 100 meter radius equals 4,000 meters per second. However, we must take the square root of this value to find the velocity. So D is our correct answer. In this video, we delineated how linear motion is affected by acceleration along the same plane by using the kinematics equations VAT, VAX, and TAX. Projectile motion applies much the same principles, but introduces trigonometry in order to resolve velocity into its horizontal and vertical components. Inclined planes are another example of linear motion. However, they involve using trigonometry to break down the force of gravity vector into its components, most importantly, Fx pointing down along the incline. Lastly, uniform circular motion was introduced with two new formulas for centripetal force and centripetal acceleration, which is a special case of constant acceleration.
Thanks for working through these 4 applications of motion with constant acceleration. As you've seen, the calculations can be a little laborious at times, but the good news is that they are widely applicable. So good luck in applying them, and happy studying.